slightly more complicated one. Now, what I would say is this chapter is usually, okay lah, we do have a lot of variation to the question also lah. But this question, for me, it's not the easiest, but it is also not the hardest. Like, it has quite a fixed method of solving. Actually, for this semester also, everything also have quite a fixed method lah, besides the mixture chapter. So you will see here. Now, so 1 kilomole of octane is burned with air that contains 20 kilomole of oxygen, as shown. So assuming the product contains only CO2, H2O, O2, and N2, determine the mole number of each gas in the product and the air-fuel ratio for this combustion process. Now, if you only look at this one, what kind of process is this? As in, what you learned in the previous slide. Is this a stoichiometric amount of air? Is this excess? Is this deficiency? Can you see just from the question? Why? How will you know 20 kilo is excess? Now, one thing to bear in mind, now this is not a best example because I say this is an easy question. Most of the time, you need to calculate in order for you to know what is the stoichiometric amount of air or theoretical amount of air that you need. Okay? Now, this example, you are correct, it is excess, but it is not because of the 20 kilomole. No, the real reason is the oxygen in the product. Does that make sense to you? You have oxygen in the product, but then you don't have CO or whatever, right? So meaning you are getting a complete combustion. You finish burning everything, but you still have oxygen. So it means that this is an excess. You have an excess air case. Okay? So, but of course the question doesn't really ask anything about this. So let's see how we solve this one. It asks you for the mole number of each gas in the product. So you need to find the number of moles for each of them. And then the air-fuel ratio. So first thing that you always need to do, you need to construct the chemical equation first. Okay, now, if you are to look for example, let's say if you need to find the stoichiometric amount, then what you do is, you don't put this here because you don't know what is the stoichiometric amount. The stoichiometric amount is always the amount of air. Then you take out this O2. Because as I said, stoichiometric amount is when you are assuming ideal process. So everything burns completely. So you take out the O2, you put a variable here, then you calculate. But I will leave that to later first. But for now, let's do this. So we know that we have 20 kilomole. So you can see this is the field. You know you have 20 kilomole of oxygen. And just now we say that because you burn with air, right? So every kilomole of oxygen will come with 3.76 kilomole of nitrogen. So 20 multiplied by this whole thing. So this whole thing here is air. And then your product, you get CO2, H2O, O2, and N2. So a lot of variables here, right? Actually, to solve this, it's actually very simple. You just need to compare left and right. Because we say that the number of atoms must be the same. So you pick the element one by one. So for example, so like this. So you pick C first. So C, right? So on the left, we have 8. Then no more. So 8 lor. On the right, there's only one C. So X. So you know X is here. Then do the same for everything. So H, on the left, we have 18. On the right, now, so here, you need to be a bit careful here because like this 18 you can put directly, but here, this is actually Y, but 2Y. So 2Y here, then Y you can 9. Then after that, O, so O also same thing. So sometimes, okay, to be safe, you can always keep it to the single element, like HO. Because sometimes when I do, I will put O2, but then if you put O2, then you need to be careful because this is just one O, something like that. So here now we put O instead of O2, so 20 times 2, then 2x, y, 2z. So you have the y value, you have the x value, you sum in, you get the z value. Then n2 is just n2 because n2 doesn't react. So 3.76 multiplied by 20 equals to w. So that is the amount of n2 that comes out. So it's just balancing left and right. It looks easy, but then this is also one part where careless mistake can creep in a lot because you have multiple calculations here. Okay, so from here, now we write out the full equation. So from here you can see that these are the number of moles of each of the products. Then we proceed to calculating air-fuel mixture. So air-fuel mixture, just now we mentioned, is mass of air over mass of fuel, right? So this is the part where you need a bit of maths here. So we look at mass of air first. So for the mass of air, so like we mentioned, air is O2 plus 3.76 N2, and we have 20 of them. So 20 multiplied by 4.76, so 1 plus 3.76, so 4.76. So this is the total number of mole for air. Okay, total number of mole. Then what is the molar mass of the air? 29. So this is a fixed value. So total number of mole multiplied by 29. So this is the mass of air. Then mass of fuel. So mass of fuel will be whatever here. Sometimes it's not as simple as that. Sometimes it can get a bit complicated. But anything other than the air on the left hand side, everything on the left hand side other than air would be the fuel. So in this case, C8 H18. So 8 multiplied by 12 because this C we have 8C. 12 is the molar mass of carbon. Now this one, right? Sometimes my solution can be a bit confusing because H actually doesn't exist as H1. H is always H2. That's why they change it to 9 multiplied by 2 instead. This is more of a technical thing lah. You do 18 times 1 is the same thing lah. Doesn't matter. H is 1. Okay, so this is the total number of mass of the fuel. So this way you get the air-fuel ratio. So when you write the air-fuel ratio, right? Yeah, sometimes my answer for tutorial can be a bit lazy. We will just write 24.2 over 1. But for you, exam, write kg air over kg fuel. Because even though they are both kg, but they are technically different quantity. Because this is for air, this is for fuel. So kg of air over kg of fuel. So just write the two things. I'm asking about 29. That's why I say hold it first. Okay, get it so far? Alright, if no question, then I'll move on. So predicting the composition of the product is relatively easy when the combustion process is assumed to be complete. Because again, if the combustion is complete, then you will always get CO2, SO2, H2O, those things. Because those are the stable elements. Like OH, they are not stable. So the only alternative we have is to measure them directly. So we have this what we call the oxide gas analyzer. So it will give you the composition. But the result is in terms of dry analysis. What do we mean by dry analysis? Later we will also talk about this, but yeah, I can talk about this. So now we actually have two types of analysis. One is considered dry analysis, one is considered as wet analysis. Dry analysis basically is this. So you can see that this is a product. So combustion will always give you this kind of product. But sometimes this H2O, right, that result of the H2O can be liquid, it can also be gas. So let's say we assume it is liquid, for example. So meaning after you burn, you get some liquid. Sometimes you do have that, maybe you don't know this. So which means, right, when you analyze the product, You only get this one. So the percentage that you get is actually only CO2, O2, and N2 without the H2O, which means that it won't be as accurate because there's no way your combustion doesn't give you H2O. But when you analyze it, it always doesn't give you H2O. Yeah, that's the story. So that will be what we call dry analysis. So the dry analysis is called percentage. So let's say if you go on full analysis, it will be 8 over total number of mole analysis. So 9 over total number of moles, something like that. So, but then because you ignore the H2O, then somehow it becomes 8 over the total but without the H2O. So the percentage will be a bit off. It won't be not 100% accurate. That is what happened with the dry analysis here. So the result that you get from the gas analyzer is actually on a dry basis. Okay, so now we look at one example here with coal. Combustion of coal with theoretical aim. Coal from Pennsylvania, which has an ultimate analysis as the following. So this coal have all of these components, as you can see, and it is burned with theoretical amount of air. Disregarding the ash content. So ash is not something that we can analyze because it's just ash. So sometimes we just ignore it, throw it away. Okay. Determine the mole fraction of the product and the apparent molar mass of the product gases. So yeah, this one come back in. And then after that, you need to determine the air-fuel ratio required for the combustion process. Okay, so do the first part. Meaning do the mole fraction and the apparent molar mass. One hole is 16. one you need to remember because you keep using it. The next time looking for value, just fix value. You need to find the mole analysis, and also, so one thing here is very common is that for this chapter, right, most of the time what you are given is in terms of mass analysis or mole analysis, which means that you don't actually get a fixed amount of number. Like, I won't tell you properly how many kg you are given. So, like some of you who might already know this, you need to assume the number of mass or mole just to find whatever that you need to find. Okay, so that is a very common thing for this chapter because again, chemical reaction is actually just ratio. More than the other number just increase. Okay, so here, now assumptions for this kind of question will be, again, for this one, for this particular one, right? 1, 2, so ideal gas is usually the assumption. 1 and 2 are very important because those are the assumptions for us to find the stoichiometric amount of air. So, of course, it probably doesn't come in the first part, it comes in the second part. So, stoichiometric, you need to assume it's stoichiometric first in order for you to be able to get the stoichiometric amount of air. Actually, 1 and 2 comes together. So, for stoichiometric amount of air, so let's say if I ask you to find, so I don't know how much first, I will say that I need to find the theoretical amount of air or the stoichiometric amount of air. The products will always be only CO2H2O. If you have S, then S2, SO2. No S, then of course no R. Then and also N2. So it will be complete combustion. So you need to assume complete combustion with no excess air in order for you to find the stoichiometric amount. Okay, so this one is very important. Because sometimes students jump straight into the actual process and then they get confused because they don't know how to find the stoichiometric amount. So we will have examples of this lah. You will see. Okay, so these are the assumptions first. So first off, now, so this question assume 100 kg of the coal rather than 1 kg, but doesn't matter. So it assume 100 kg of the mole. So based on that percentage, you can find their respective kilomole. We ignore the ash because ash is non-combustible. You just go in and it comes out. So we ignore the ash. But it is still part of the coal. Okay, just that we ignore it. So your value should be about the same, but then with 2 extra zeros to the left. Okay. So now, so based on these assumptions, you can write out the chemical equation here. So this chemical equation you can see is a little bit long when you're doing coal because you have too many things. You have C, you have H2, you have O2, you have N2, you have S. Alright, so now, why do we want to find the mole fraction? Always remember this. Chemical equation is based on number of mole. It's not based on number of mass. So what you get just now was mass analysis, right? So you cannot just assume 100 or 1 kg and then sub in the value into here because that is based on mass. This equation must be based on mole. So we convert them to mole analysis or mole, then we put in the value into the equation. So that is the main reason why we did the mole fraction. Or not really mole fraction. That's the whole reason why we find the mole. Okay, so you sub in, then we assume stoichiometric. So we do not know what is the theoretical amount, that's why it's not ATH. We do not know what is the stoichiometric amount. So to find the stoichiometric amount, we assume complete combustion. So CO2, H2O, SO2, N2. That's all. No other thing. Then we want to find ATH. Okay, I'll move on to the next slide. Okay, so we carry over this equation. So based on this equation here, once again we do the entire balance here. So for solid field, actually the balancing is quite straightforward because we already split the CH as out and O2. The only thing that you need to be a bit careful here is this. For N2, you actually, N2 is not just 3.76 multiplied by the amount N, because there is N2 in the code itself. So this is also one misleading mistake, because we are so used to N2 is just the amount, N2 in the N. But this time that there is N2 in the field. So there's one extra term here. So O2 also same balancing. So by balancing this, you can get ATH equals to 7.393. So meaning that is the exact amount of air that you need for complete combustion. Okay, so from here you can sub in all these values into this equation, then it looks something like this, a bit complicated, but yeah. So now, what was the question asking again? Let's see. The apparent molar mass I think we found at the end, but here you need to determine the air-fuel ratio required for this combustion. But I don't think, oh wait, this question again, let's see. Now we look back at the first part first. So just now I read the question a bit wrongly, that's why I asked you to do a wrong thing. Determine the mole fractions of the products. Meaning, right, actually you are supposed to find the mole fraction over here. Meaning the product, what are the mole fractions? But never mind, because I thought it answers you to find out the mole, which is what you need to find also. So, to find the mole fraction of the product, then very straightforward. It is actually exactly what I told you just now about the gas analysis, but of course this one you include the water lah. So meaning this way. So for the product, total number of mole for the product would be, you look at the product, so 7.03, 0.945, 0.0278, and 27.82. So all of these are the products. Okay, so you total them up. Then for their mole analysis, then it's just mole analysis of just the Y. So for CO2, then it will be this, H2O, SO2, N2. So usually N2 will have the highest amount. And also just for you to double check, after you find this mole, let's say the product, right? Just add another one and see if you get one. If you don't get one, then something wrong. So we found the mole analysis of the product. Then from here, you can also find the. So from here you can also find the apparent molar mass of the product. So the number of moles at the bottom, on top should be the mass of the product. So for the product, yeah, you need to find their respective mass, and then you can get the molar mass. And then for the air-fuel ratio, so same thing at the top. You need 7.393 amount of air multiplied by 4.76 multiplied by 29. But for the fuel, you don't need to total up anymore because you assume 100 kg of coal when you calculated the mole. So those came from 100 kg of fuel. So you just put in 100 kg. Even though we say disregard ash, ash is still part of the coal. So here we can just use 100 kg directly. Then you can get the FU ratio of the of this combustion. So 10.2 kg of air is supplied for each kg of coal in the furnace. So we could also solve this problem by considering just 1 kg of coal and still obtain the same result, because like I said, they are all just ratio actually. So, but then we will have to deal with very small fractions in calculation in this case, so just like what we do. Enthalpy of combustion. Okay, so a bit more energy lah. Determine the enthalpy of combustion of liquid octane at 25 degrees Celsius and 1 atm using enthalpy of formation data from table A26. Assume the water in the product is in the liquid form. Okay, so now this case is not as straightforward as what we have just now, because you actually do not know what is the amount of air here. So what you need to do, actually, you need to start off by calculating the equation first. I mean, you need to start off by calculating the actual amount of everything first. What do I mean by that? So this. Now, we are not going to the table A26 here. So we just take the value from table A26 just now, from the table A26. So CO2 is that value, H2O is that value in liquid form. And of course, this time, since your reactant is C8H18, not C like just now, so C8H18 has its own enthalpy of formation as well. Okay, so if you go to table A26, actually I don't know whether this one has an example here. Yeah, here we only have CO2 and H2O, we don't really have the C8H18, so no choice. So this, you will get this value from the table. So first thing you need to know, again, we need to find out what is the amount of each of the elements. So just like what we did in the previous example, you find the stoichiometric amount of the air first. So we found the equation just like usual, or just like just now, CaH18 plus air. Then for stoichiometric amount, you only get CO2, H2O, and 2. So this one we explained just now, so this is why the matter anymore. So these are the steady elements. So at 25 degrees Celsius, 1 atm, their formation is just 0. So both reactants and products are at the standard reference state of 25 degrees Celsius and 1 atm. Okay, so now, okay, I think here we skip a little bit here. Now, this 8, 9, and 3.76 ATH, so this 8 and 9, you still need to do a bit of the balancing that I showed just now in order for you to get that value, because those are not from the question itself. Okay, the 8, so you balance C to get 8, you balance the H to get 9. Okay, so originally these two are not known, you only know this one. So you balance, you will get 8 and 9. Now, we didn't bother to solve the ATH. We also didn't bother to solve the 2.76 ATH. Why is that the case? Because we don't need that. Because in this case, we are looking for enthalpy of combustion. Since their formation value is 0, even if you found them, they are 0 anyway. So we don't need that. So we only need to find what we need. So again, Enthalpy of combustion is just the enthalpy of the product minus the reactant. So in this case, the product, we have CO2, we have H2O, that's all, because N2 is 0. Reactant, we have CaH18, air is also 0. So these are all we have. But we need, of course, we need to include the mole because the value itself is in terms of kilomole. Something to be here. Then shouldn't the final answer be kilojoule. But anyway, yeah. So here you use the 8 kilomole of the CO2 multiplied by the combustion, the enthalpy of formation of CO2. Then you use 9 multiplied by the enthalpy formation of H2O. Then reactant 1 of the CaH18. So then you can find out what is the answer here. So this is the, okay, so now even though we included all the kilomole there, right, we still maintain this mainly because of this term. So I mentioned just now, chemical reaction equation is actually just ratio. CaH18, and let's say if we have 2 CaH18, then all these value will change, right? So technically speaking, this value is, so for every kilomole of CaH18, because we are calculating based on 1 kilomole of CaH18, you will get this much energy. So here, they just multiply with the molar mass, they just divide by the molar mass in order to convert it to kilojoule per kg. That's all. They want to find out what is per kg. So let's see if the question says anything. Yeah, the question actually didn't say what they want in terms of kilomole or kilogram, so it doesn't matter. So this is it. So this equation is always, so the value that you get from the table is always in terms of kilomole. So if you want to change to kilogram, then you divide by the molar mass. Wait, then you multiply by divide by the molar mass, correct? Because it's per kilomole. So you do divide by 891. This one, you need to balance this chemical equation. I didn't show the balancing steps, but it is there. So 8 CO2, 9 H2O. But you need to balance this out. Originally, you don't know how much CO and H2O. Okay, so this 8 and this 9 is just from there. So this way, you can get the enthalpy of combustion. Okay. Okay, we will look a little bit on energy balance analysis. Okay, so just now is the simpler version. So this regarding any changes in kinetic and potential energies. The energy change of the system during a chemical reaction is due to a change in the state and a change in chemical composition. So basically, this is the extra thing that we are learning here. So all this while when we use table refer to answer, this is the one that we do. So now with chemical reaction, we got this extra thing because there is a change in the bonding, basically. But in general, the way that we solve this is still about the same. So energy balance for open system. So let's say combustion, we have open system. So steady flow open system, we say E equals to E out, we write this equation out. Then since this is a combustion, then you can just cancel off this one. Okay. You can just cancel out the work and also Q in because combustion, right? So ultimately you are left with Q out and then H product minus H reactant, which was what we said just now. So the H product minus H reactant sometimes can get a little bit more complicated in the sense that, so now we expand it further, so this is for the reactant, this is for the product. Then the enthalpy will involve 3 terms. So the equation just now that I showed you with the enthalpy of formation is only the chemical reaction. So now we include back the change in the state like what we do in normal thermo. So this will be the one for normal state and this will be the enthalpy of formation. So again, actually we will have table for this one, and later you will see how we do. So they are all at 21 degrees Celsius, 1 atm. Then later we will see how we use this. So this is the open system equation. Okay, so H is equal to the, again, enthalpy of formation. So this is the enthalpy for the chemical reaction. This is the sensible enthalpy change. So what is the final enthalpy minus the enthalpy at the reference state, which is 25, 1 atm. Basically that. Looks complicated, right? Later you will see actually it's actually quite easier, but then in a way you need to memorize how to do this. Okay, now I keep saying that combustion reaction is an open system. So why do I have a closed system example here on how to solve this question? So can anyone tell me, can anyone give me an example of a combustion process in a closed system? That one technically is also an open system. We assume closed system only, but it's technically open system. Huh? Oven. You burn things in oven. Yeah, you burn things in oven. No, right? You heat it up only, right? No, this is combustion. It must involve reactions. An example of a closed system combustion.
Furnace can.
Huh?
Furnace.
Furnace is also open system. Right? I mean, you can even see burning.
Industrial.
No one. When you supply air, it's also from outside. Right? It doesn't happen inside. That's why I say engine technically is open system one. It's just that we can make it a closed system when we analyze. A bomb. A bomb is an example of a combustion closed system. Because it explodes, the combustion happens right before it explodes. So when it explodes, of course it bursts out, but then the whole process actually happens inside. So bomb is actually an example. So our last example here, which I think I will discuss tomorrow, not today. The last example here actually will show you the bomb example. Okay. So now if we have a closed system, now unfortunately enthalpy of formation, they are all enthalpy. We don't really have internal energy. So now we do the usual closed system analysis. So Q minus W equals to delta U. And we use back the same equation just now as the H. So U of formation, U minus U delta, then RU delta. But since we don't have value for internal energy, we convert this to enthalpy, but we minus PV. How does this work? Because we know U equals to H plus PV. So basically we just move PV over that. So then we change this whole thing to H. Hey, sorry, I wrote the no wonder it looks good. H equals to U plus PV. It's already correct. So we move the PV over here, but of course this is what we do. PV can be negligible if you are dealing with solid and liquid, and can be replaced by RT for ideal gases. So PV is not a value that we usually will have, so we will usually change it to RT instead. So RUT then easy, because you just need the temperature of combustion. Then RU is just universal gas constant. PV is hard to find, so usually that will become RUT. Okay, so we will look at just one last example, then we will stop, then I will finish this up tomorrow. So here we have a liquid propane, which enters a combustion chamber at 25 degrees Celsius at a rate of 0.05 kg per minute, and it's mixed and burned with 50% excess air. So this one we have excess air that enters the combustion chamber at 7 degrees Celsius. An analysis of the combustion gases reveals that all the hydrogen in the fuel burns to H2O, but only 90% of the carbon burns to CO2, with the remaining 10% forming CO. So this example is also one where is also one where we have an excess air, but somehow we have incomplete combustion. Remember I told you this can happen? So this is one of the examples. So if the exit temperature of the combustion gases is 1500 Kelvin, determine the mass flow rate of air and the rate of heat transfer from the combustion chamber. Okay, good. Okay, so here so this is an incomplete combustion, but you do know a lot of things where they tell you H2O is completely burned. 90% of the carbon go to CO2, 10% of the carbon go to CO. Okay, so assumption, standard assumption. So then the chemical equation here, you can actually, now you can see here that, do you see something weird here basically? Actually, I'm thinking maybe I should discuss this tomorrow. Yeah, I think we can do it tomorrow. But one thing here, you can see, never mind, tomorrow. We will next 2 months, rest of the paper.